Most of us in electronic engineering have done radio at some point in our lives. It was pretty cool, wasn't it? I kind of miss all of those big glowing tube contraptions and backyard towers with various antennas poking out everywhere. It was a little romantic in a nerdy kind of way. These days, though, radio is becoming software-defined. What? Are we now reduced to debugging out a few lines of code instead of climbing a pole with our SWR meter to see what's wrong? Where is the nerd romance and all of that? Hi, I'm Amelia Dalton, host of Chalk Talk. Fortunately, SDR, that's Software Defined Radio, has a lot of interesting and challenging problems that don't involve climbing dangerous structures with SWR meters. And they involve hardware. My guest today is Noam Levine from MathWorks, and we're going to talk about targeting SDR to hardware, the way the cool kids are doing it these days. And before we get started, don't forget to click that link. There you can find out more information about software-defined radio solutions from MathWorks. Hi, Noam. Thank you so much for joining me today.
Thank you, Amelia. Happy to be here.
So I've been hearing about SDR for years, but who exactly are we talking to today?
Well, today we're going to be talking to several different groups of people.
Okay.
That includes algorithm developers, your modem designers, and waveform developers, along with your systems engineers, systems integrators, and finally your RF engineers as well.
Noam, that's a lot of different stuff going on. How can we boost efficiencies in the design process?
Well, we've got a goal for that. And our goal is to create a common design environment in MATLAB and Simulink that will span all of those multiple design disciplines, which typically happen across multiple teams in a company. And we're going to be targeting some off-the-shelf hardware for prototype development with a path to production.
Okay, so this seems like it should be kind of a big deal.
We think it is. And it's a big deal because radios really are everywhere.
Yeah.
And it's not just the traditional communications equipment that you'd think of, like tactical radios or airborne or spaceborne communications equipment, but we're seeing a lot of new applications as well, including medical devices, remote sensing and monitoring, and all of those things that keep getting connected to the internet every day. A lot of them need radios.
Absolutely. So it seems like this is quite a diverse group of engineers. Are they all coming at this problem in the same way?
No, they're not. The different engineers are coming at SDR development from a lot of different angles. The systems engineers and RF engineers are really looking at the system performance. And a lot of times they're going to want to characterize that system performance before they have the hardware available to them.
Sure.
So they're going to want to model their system to verify the performance, and then also test and verify that performance on hardware during their prototype and production phases. The algorithm developers are worried more about, how am I going to process that data? What does my algorithm look like when I get signals in? So they need to design and simulate the radio algorithms, sometimes independent of the hardware.
Sure.
But then they're also going to want to see, how does my design work on hardware? But they may not have the FPGA or HDL expertise to do their own hardware development. And they may not be able to beg, borrow, or steal the resources from other groups to do that. So we want to give them the tools that allow them to test their own algorithms on hardware by themselves.
Sure. So, Noam, given all that, what does this design process look like?
Well, the design workflow consists of modeling and simulation of the RF signal chain, modeling and simulation of the communications algorithms, and then we're going to test those algorithms with real-world data, and then finally deploy that to hardware for prototyping and production.
So this seems like a really expansive problem that covers a lot of ground.
It does, and that's why we didn't go about this alone. We worked with a number of our partners in the semiconductor and distribution world, specifically in this example, Analog Devices Avnet, and Xilinx to come up with an integrated workflow, because we have a lot of disciplines that are needed in order to implement this design. You've got to understand everything from RF through FPGA design to know how to write Linux kernels.
Right.
So by working together, all of us were able to create the hardware support packages, and system-level examples to help these engineers get up and running, along with training and consulting services to really help folks get their designs into production.
Cool.
Because again, that goal we're trying to reach is that common design environment that allows all of those disciplines to work together, speak the same language, and get something up and running on hardware.
Okay, Noam, let's dive into this thing.
Okay, so the way this process is going to work is we're going to start by simulating our entire system in MATLAB and Simulink, everything from the RF through the baseband, and monitor and measure everything.
Okay.
Once we get everything working in simulation, now we're going to test our algorithms with real data coming off of our real RF transceiver.
Okay.
Once we get that up and running, we can deploy our algorithms onto that Zinc device, still tethered to MATLAB and Simulink for test and verification and parameter tuning. And then when that's all done, we can finally deploy to a standalone environment.
Okay.
So let's start the process and look at everything in simulation.
Sounds good.
And the way we're going to start this is we're going to start by looking at the RF transceiver. Now, the transceiver we're going to be looking at in this example is the AD9361 RF Agile transceiver from Analog Devices.
Okay.
It's a highly configurable device, so it's got a very wide tuning range from 70 megahertz to 6 gigahertz. It's got programmable channel bandwidths. It's got lots of programmable filters. It's got ADCs, DACs, mixers, a whole bunch of stuff. It's a very complex part, but a very capable part. So with all that complexity comes a set of challenges of its own. There's on the order of 1,000 programmable registers in this device in order to make it fly.
Wow. That looks about 999 ways it could go wrong, too, Noam.
That's right. And hopefully one way to get it right. And the way we're going to help folks get that right is through a system-level model of that device. So what we've created is a multi-domain model of the entire AD9361 transceiver. In this example, we'll be looking at the receive path for the sake of time. But even there, you've got tunable RF receivers, and we've had to model all of the different parameters that you have to worry about in RF.
Yeah.
We've got a third order delta sigma ADC. We've got programmable analog and digital filters. We've got automatic gain control. And we had to trade off the fidelity of our modeling with simulation time. So we're not talking a transistor level model here, because nobody wants to sit around for weeks and weeks to simulate frames of data.
Right.
It's a behavioral model where we can get an LTE frame through the device in a matter of minutes.
Cool.
And the behavior of the model was verified against the actual silicon in Analog Devices lab.
All right, Noam, so we're all engineers here. Can we dive in and get some details?
Sure. So this is what the model looks like for the 9361 receive path.
Okay.
So at a functional level, we've modeled your automatic gain control, and we've done that through a time-triggered state machine. We've got programmable gain tables that you can also edit. There's analog continuous time programmable filters. There's digital filters. We've got our ADC, and we've got a number of power metering stages. And the beauty of having this all in a model is, as your system is running, you can take a look at what's going on in your RF signal chain. You can take a look at what's going on in your gain stages. And that's something that you simply can't do with a chip sitting on a printed circuit board.
Sure.
So having the model is one thing, but you really need to see how that's going to work in system.
Sure.
So as an example, we'll provide you an RF test bench. So you can put your 9361 model down into an environment where you can throw any test signal you care to think about at it. We've got examples of continuous tones and LTE-like signals, and you can really see how the part is going to react. You also have the ability in this environment to customize the filters on the 9361. You can set up your own test signals if you want. Anything you can dream up, whether you can physically produce it in an actual lab or not, if you can describe it in MATLAB or Simulink, you can test the device against those kinds of waveforms.
Cool.
So once you understand how the part itself is going to react, the more fun comes when you put that part into a system. So for this example, we're going to be looking at a QPSK receiver model.
Okay.
And this is something that's out of our examples in our communication system toolbox. So we can build a simulation test bench that has both our 9361 model and our QPSK receiver, so we can see how our algorithm responds with simulated data coming out of our 9361.
Very cool.
Okay, so here we have our 9361 model running in simulation with our QPSK receiver model. We've put it in an RF test bench so that you can have your QPSK transmitter source, but you can also throw in other signals. In this case, we've got a CW source, and the idea here is that you want to be able to mimic any of the nastiness you might find in your real communications channel. So we can see our transmit spectrum here. We have our nice QPSK signal, and we've got a couple of these CW interferers. On the receive spectrum, though, we can see that the 9361 has done a good job of getting rid of those tones that are outside our band of interest. I've got some knobs here that I can tweak on my test bench, so I can change the power settings. And these numbers you see scrolling by are data that's being transmitted from our QPSK transmitter, saying hello world over and over again. The fun thing we can do is we can take a look while this is running, look at what the internal states of our 9361 receiver are in this case. So just at this level, we've got some output gain values. We've got some thresholds that we can look at. And everything's running nicely within spec at this point. This model is set up to keep our output power at around minus 11 dB. So let's go and mess with things a little bit. So what happens, say, if we crank the power up on our QPSK transmitter? We can go back into our model. You can see our gain has jumped way up there, but it's starting to come down. And you can see that the index here, this is a gain index, is changing. And if we watch our state machine, which is how we're modeling our automatic gain control, we can see that it's going through its steps to decrease the gain to get us back to where we need to be. Similarly, if we want to have some more fun, we can turn things down. Check to see, are we at threshold limits? Yeah, we're at some lower threshold limits here. So our gain control is again re-indexing through the gain, and our gains are slowly rising. So this is just a simple example. You can see that we're still receiving data. Our constellation's kind of gone away for a little while until we resync things. But this is a great way that you can model what your system is going to look like and model any channel impairments that you might have in your system before you even get your hardware.
Okay, Noam, so far we've been working on simulated data, but what about the real stuff?
Sure. Now that we understand how our algorithm is going to work with simulated data, we're going to connect our hardware to MATLAB and Simulink and pull data straight off of that 9361 and bring it into our computer. And we're going to do that using a product from MathWorks called the Communication System Toolbox.
Okay.
And that provides a support package for 9361 and Zinc-based radios and allows you to bring that data very easily into MATLAB and Simulink. So that device we're going to be looking at is really a radio front end to MATLAB and Simulink.
Okay.
We're not really going to be running any code on the Zinc that's sitting on our radio platform. It's going to be sitting there just to packetize the data and send it up over Ethernet to MATLAB and Simulink. And we can take a look at what that looks like. So we're going to be looking at the same QPSK receiver algorithm that we looked at in the full simulation example, except instead of a simulated AD9361, we've got this SDR receiver block that allows us to set parameters on the actual hardware and configures our communications between the 9361 and MATLAB and Simulink. And when we run that, we can see, let's bring in our constellation here, so we can see that we've got real data coming in to our algorithmic model, and we can see those lovely hello worlds that are streaming by. And they're all moving a lot faster than they were when we were simulating everything, because now we're just simulating the algorithm and not both the algorithm and the transceiver.
Okay, so now that we've got all that algorithmic stuff working, how do we get it into our FPGA and still talk to MATLAB and Simulink?
It's a great question. The next step in the process is developing that prototype with real-time data logging and parameter tuning.
Okay.
So the first thing we need to do is we need to get our algorithm that we've been looking at in simulation into HDL. We're going to be dropping that onto the programmable logic part of our Zinc device. And in order to do that, we've got to go through a few steps. Up till now, we've been looking at our algorithms as floating point things.
Yeah.
Simulink is inherently a floating point tool. FPGAs are inherently fixed point things. So the first thing we need to do is convert our model to fixed point data types.
Okay.
Once we've converted our model to fixed point, we can elaborate that design for more efficient hardware implementation. So the analogy I like to use is it's similar in theory to, say, if you're writing C code for a PC versus C code to run an embedded processor. You're going to write your C code a little differently because you have to worry about real world things like memory.
Mm-hmm.
Same thing with your modeling for HDL. You can do things that are great mathematically, but they might be expensive when it comes time to convert them to gates.
Okay.
So for example, do you need to do a full FFT when maybe a frequency approximation would get you the same result, but be a lot more hardware efficient?
Okay.
So you're going to look through your model and look for those types of opportunities. Then you're going to generate and synthesize the HDL code, and we'll walk through that process. When you're done with that, you can optimize your HDL performance. And at every step in the process, you're going to be testing and verifying against that original floating point design so that you know you haven't broken anything along the way and that the performance that you get is going to be equivalent to, or at least within specs, of what your design specifications called for.
Right. Okay, so let's dive in and look at that.
Sure. This is our HDL-Optimized QPSK receiver, and this is also out of our examples. At the top level, it doesn't look much different, but if we were to dive into it, we'll see that in some of these blocks, like the coarse frequency compensation, for example, we actually have replaced an FFT with a frequency approximation.
Ah, okay.
We're going to take that receiver, and now we can drop that into a higher level model that we're going to target to our device. And in this case, we've actually put it into a little bit of a larger system that's going to do both the transmit and receive. And we've got some other blocks around it that will allow you to do things like change your transmit source. So if you want to play with what signals are coming into your algorithm while it's running on hardware, we've modeled that here so that you'll have the opportunity later while it's running to interact with the model.
Okay.
And we'll show that in a minute. But the first thing we need to do is figure out which of these things is going to run on that programmable logic on the Zinc and what's going to run on the ARM processing system. So we're actually just going to take all that stuff in the middle, all of our HDL algorithms, and that's what we're going to run on programmable logic.
Okay.
The rest of this, we're going to run on our ARM processing system.
Gotcha.
So the first thing we need to do is get all that algorithm stuff and convert it to HDL or generate HDL code from it. And we're going to do that using something called the HDL Workflow Advisor, which is part of HDL Coder.
Okay.
And what HDL Coder gives you is a step-by-step process for generating that HDL from your Simulink model.
Okay.
This is the first step of the process where we choose what kind of workflow we're doing. And in this case, we're doing an IP core generation workflow. We said at the beginning that we want a path to production. Well, here's where we can tell HDL Coder that what we want to get out at the end of the day is an IP core.
Right.
So this HDL IP core, when we're done with it, is something that, yes, you can use it in MATLAB and Simulink, but it's an HDL IP core that you can then bring into other downstream tools, say like Vivado IP Integrator, for inclusion into a larger production system.
Okay, Noam, so what does the code look like?
Well, when we generate HDL, we generate a few things in addition to the code. First thing we do is some reporting, and this we can get not only some information about the HDL we've produced, including resource estimation, but we generate the code itself. So this is what our HDL code looks like. It's readable code. And the one thing you might also see before every little chunk of code is what looks like a hyperlink.
Yeah.
And that is a hyperlink back to the model.
Oh.
So we have full traceability both from code to model and from model to code. So if you're worried about design reviews, standards compliance like DO-254 down the road or things like that, we provide a direct line from your model, which is tied to your specifications, down to your code. So we've got an unbroken chain, if you will, from specification down to code.
Very cool.
Once your code is generated, We will also automate the Vivado project generation.
Very good.
Now, this is handy for those folks, those algorithm developers that might not be as familiar with HDL tool flows. This will allow them to get their project at least up and running and get something on hardware that they can look at without having to go find the FPGA tools expert down the hall or in the other building
Right.
to help them with their project. And the final step in the process for at least the HDL side is the Bitstream generation.
Okay.
So again, that gets all scripted in the background, all the synthesis, place and route, and then download to the hardware, and we start that running.
Okay, so what's the ARM part of the story here?
Well, the ARM part is something we call a software interface model.
Okay.
So if you remember from our top level design, we had all that algorithmic stuff in the middle, and then we had all those blocks on the outside that were going to control certain things, like our transmission source. You can build whatever sort of knobs or buttons or dials you want in your design, things that you know you want to use to control the actions of what's going on your hardware.
Yeah.
And so with that, we develop a software interface model, which is all about the goes intas and goes outas from the ARM to the FPGA.
Okay.
And behind that ends up a lot of generation for AXI interface code. So it's both instantiating AXI interfaces on the HDL side and generating all of those Linux drivers on the ARM side that know how to talk AXI so you can control things. And we run it in something called external mode.
Okay.
And this is a feature of our embedded C code generation, our embedded coder product. So while this is running on hardware, all of the switches that you've put into your design, all of the knobs, all of the sliders or whatever, you can mess with those while things are running on your board. So if there's parameters you need to change and fine tune, if there's shocks you want to give to your system and see how it responds,
Yeah.
those are all things you can set up in your top level model and work with your ARM device and see how it's going to react.
Very cool. Okay, so the last step you said was optimizing the HDL, I think. Are there some knobs I can turn here?
Absolutely. So again, if you're that algorithm developer just looking to get something up and running, great. You can run through our whole process, maybe leave all the default settings. If it's maybe not running as fast as you'd like it, or maybe it's using a few more gates than you'd like it to do,
Yeah.
there's a lot of knobs you can turn within HDL Coder that will optimize your code generation either for speed or for area or a combination of both.
Cool. Okay.
So again, all of that gets down to the running tethered,
Yep.
which is what we've just been doing. But now we have this IP core. So now you can take that IP core, bring that into other downstream tools, and you can end up with a standalone system.
Very cool. All right, so I don't know about my audience, but I need to recap. Noam, help me out here.
Sure. So what we've talked about is a system design workflow that goes all the way from modeling and simulation through hardware deployment. It's something that enables rapid prototyping without requiring a lot of knowledge of either HDL or the FPGA tools. And it's a single environment that incorporates all of those system elements. So we've simulated RF and we've looked at RF signal chains. We've designed algorithms and played with those. We've done FPGA programming, and we've also been able to develop that software interface between your ARM and your FPGA.
All right, this sounds a bit too easy. Do I just press a couple buttons and poof, there's my design, Noam? What's going on here?
I wish that were the case. I don't want to set the impression that this is a magic button that you press one thing and poof, out comes your fully optimized radio design that you can go to production with.
That'd be fabulous.
It would. There's a lot of work involved. This has been a pretty broad brush overview of all of these design elements. We could spend days, if we wanted to, on each of those elements. We can get into the real nitty-gritty of RF design and simulation. We've got folks that would love to talk about that stuff.
I bet.
We've got whole training courses on HDL Coder and how to turn all those knobs to get optimal performance. So, no, there is a lot of work to do. What we're trying to do is provide a framework and a process that makes that easier for you and maybe helps the different design groups in your company maybe communicate a little better, maybe talk together and get a little more efficient in the process.
And I think we all need that at some point or another. I think I'm ready to get started. So where would I go for more information?
Well, you would go to mathworks.com/SDR, and there you can find white papers, videos, examples, request trial software, and all that stuff to help you get started on your SDR design.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Noam.
Thank you. It's been a pleasure.
And before we go, don't forget to click that link. There you can find out more information about software-defined radio solutions from MathWorks.